Hello! Since last time we just talked about why we need a type 2 PL, we can spend more time to continue the charge pump PL and its design insights. Then, what's the obvious design change in a charge pump PL? Correct, charge pump. So, there are lots of different topologies of charge pump, and we could start with the traditional one with the source switching. As you can see, when the down signal of the PFD output goes high, the down current will pull out of the filter through the current meter set I down. Then, charge on the filter will be pulled out and decrease the tuning voltage of the VCO, slow it down. On the other hand, when the up signal of the PFD output goes high and up bar goes low, the up current will be pushed into the loop filter. Then we can push the charge on the filter and increase the tuning voltage of the VCO and speed up. From the combined operations of the PFD and charge pump, you can derive the transfer function of the net current to the loop through the input phase error between the VCO and reference clock. So, do you see any issue here? Think about the control voltage images for 5 seconds. Bingo! The control voltage of VCO means the output of the charge pump could be moved up and down, which may match VCO's transfer curve of the frequency versus voltage to make sure the VCO has enough frequency tuning range and good phase noise. We may want the VCO's input swing as big as possible, which will reduce the headroom of the charge pump. Especially, the supply is reduced a lot in the advanced technology. What else? Think about the accuracy of the I up and I down for 5 seconds. Yes, either the I up or I down current came from the current meter. We've known the meter will have the current mismatch, so that would cause a different I up and I up down currents. What happened to the mismatch current here? Right, from the ideal lock condition, you should realize that's not sustainable since there's a charge pump mismatch here. So, in a real case, the PO should lock with a static phase error if there's a charge pump mismatch, such that the charge would be balanced. Positive charge equal the negative charge, and then I up times phase offset equals I down times the reset phase. Then you should see the control voltage will go up and down later in each reference period. The voltage ripple on the VCO control voltage causes a reference spur in the frequency domain, which is the reference clock frequency offset from the carrier over VCO's peak frequency. So, again, this charge pump mismatch not only adds the reference spur jitter in a wireline time domain, but also adds the reference spur tone interference in a wireless frequency domain. Obviously, to minimize the spur, we must reduce the charge pump mismatch. As I mentioned, people spend lots of time improving the charge pump mismatch. Therefore, let's go through some of the previous works. The first one could be simply just improving the DC current matching. But we cannot add any cascade device since we don't have much headroom in the low supply and wide tuning voltage range. What can we do? Correct. We can apply a gain boosting image as shown here by placing the OTA in the negative feedback loop, even though the down current will still vary with the tune voltage due to the limited headroom. But the up current I up will track the change through the negative feedback loop. So we would reduce the reference spur low enough since the I up minus I down is very little now. Again, if we keep reducing the supply voltage in the advanced technology down to 3 or 2 nanometer, what can we do? Think about the switching images for 5 seconds. Bingo! We can remove the source switch at PMOS and NMOS for the up and down respectively. Then all the headroom is reserved for the current source only. How do we control the up and down current? Yes, just apply the gate switching to pass the meter voltage or ground. In addition, the up and down switch may be much faster than the source switch now, such that we could reduce the turn-on time for the overlap time that you need in the up and down passes. Then we will reduce the charge pump noise further. Please be advised, the gain boosting is still reduce the up-down current mismatch in the balancing here. But if there is a device mismatch for the local variability, the current tracking ability will be limited. What can we do? Yes, we still can do something like this smart idea, which requires a sense and trimming procedure. So we send the up current into the tune node or into the filter, and we also pull out the down current. When we don't send the down current into the loop filter, we send the down current into a down capacitor shown here. For example, if the up and down current are now well matched, the error will be integrated on this capacitor. Then the error will be sensed by this V2I converter to adjust either the up current or the down current such that the currents can be matched. Again, through this negative feedback loop, from sensing to adjusting the current, either the device mismatch or the channel length modulation compensated at the same time to achieve the matched up and down current. Here are a summarized image of why we need to be careful about the design insights of charge pump PLL. The charge pump is an interface of converting the late, early phase between the VCO and reference clock phase into the up or down current to charge up or pull down the VCO control voltage to speed up or slow down the phase. We must have a design trade-off between the VCO and charge pump. For example, this VCO's wide tuning voltage can increase the tuning frequency range while keep a low phase noise with a low kVCO gain. However, that means the charge pump may not have enough headroom, especially in the most advanced technology, like 3 or 2 nanometer. Therefore, the charge pump may suffer from the current mismatch due to the channel length modulation without adding a cascade device. What we could do is to add a gain boosting to reduce the current mismatch and reference blur as little as possible. But we still see the device mismatch issue. So another way of sensing and tuning in a negative feedback loop can mitigate both the undiagnosed local variability and channel length maturation issues and reduce the current mismatch effectively. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and appreciate your comments down below. Lastly, please share the video link with the people who may be better from it.